Good morning, good afternoon, good evening. My name is Marty Fulton. I'm with the SNIA Solid State Storage Initiative. I'm substituting for our chair, Alex McDonald, today to welcome you to what a year it was and where we need to go in emerging memory. I'm very pleased to introduce our two speakers today. I'm sure that you know them very well. Tom Coughlin, who is the president of Coughlin's Associates, a longtime SNIA member and contributor, and Jim Handy, the general director of Objective Analysis, also a longtime SNIA contributor and participant in webcasts. I've been able to preview the slides, and you're going to be treated to a very dynamic presentation where these two gentlemen are going to speak on where we came from in 2019 on persistent memory and emerging memory and where we're going in 2020. So first, I would like to share a little bit about the SNIA Solid State Storage Initiative. We're an initiative of the Storage Networking Industry Association, and we cover solid state storage, persistent memory, and soon, in 2020, we're going to be covering computational storage. So we'll be looking forward to some webcasts on that topic. We'd like you to join us in January and February for some exciting events that are upcoming on our on SNIA. The first is our Persistent Memory Hackathon. We will have one on January 22nd at the Hyatt Regency Santa Clara from 1 to 5 p.m. We'll be doing a tutorial on persistent memory and then the ability to write live code to a persistent memory system in the cloud. And it's very exciting. This will be about the 6th hackathon that we've done. We have new materials at each hackathon. And if you're in the Santa Clara area, we hope you'll come and join us. It's complimentary and registration is on the PM Hackathon site. In addition, we'll be having our first Persistent Memory Hackathon in EMEA in Tel Aviv, Israel, as part of the Storage Developer Conference in EMEA, and that'll be February 4th, 2020, all day long. So you'll be able to register at the SDC site. You can find the information on the link that's above this information, the SNIA.org/PM Hackathon. In addition, we invite all the attendees to complimentary registration for the SNIA Persistent Memory Summit, which is a week from this Thursday, January 23rd, at the Hyatt Regency Santa Clara. We will have a keynote by Andy Bechtelsheim of Arista Networks, complimentary registration. We hope you'll take advantage of our day. We serve breakfast, lunch, and a networking reception in the evening. You'll have a chance to hear presentations by leading speakers in the industry and also tour some demonstrations of current persistent memory systems. So I'm going to turn it over to Tom and to Jim. We will be posting the presentation on our educational library, SNIA.org/educational library. There's a question that asked. Please ask a question. Click the question button and be sure to rate our presentation at the end. That gives us feedback for presenting the kinds of things that we think you will be interested in. So now I'm going to forward to the next slide and turn it over to Tom and to Jim. Take it away.
Well, thank you very much, Marty. Appreciate that. We're going to do the questions at the end just to make sure we can get through everything, but you're welcome to post questions as we go through it. So Jim and I are going to be, sorry, we got the, who?
Yeah, it starts with that.
So we're going to talk about mini memory types here. We're going to talk about MRAM, phase change memory, resistive RAM, and ferroelectric RAM. The abbreviations sometimes differ from the ones shown here, but these are commonly used abbreviations for these technologies. And but the interesting thing about all these emerging memories is first of all, they've been around for quite a while in terms of research and development work and even some products, and they're all persistent. That means that when the power is off, the data stays on, and they're all talked about in our emerging memories report. And I'm turning it over to Jim. Jim.
Okay, thanks. Yeah, we're the emerging memories report. We'll give detail on that on the very end of the presentation, but basically everything that comes in this presentation is derived from that. So, you know, we'll talk about, this is our agenda for the presentation. We're going to be talking about SNIA support and a little bit about Optane DIMMs, because it was back in April of 2019 that Optane was first became available in DIMMs.
I think I need to get close.
And then Tom will talk about new MRAM types, and then I'll come back and talk to you about business conditions. And then we'll talk a little bit about what needs to be done in the future to bring persistent memory into mainstream applications.
And yeah.
So with regards to hardware, there's been a lot of work that's gone on with various organizations that work more in the hardware space for these things. JEDIC has been a very important influencer on that and supported early development. There are still ongoing requirements, though, for things to be developed, including form factors and interfaces. On the software side, which Tom will be speaking about soon, we've got support from SNIA and from other organizations that have provided operating system support. That's the first and most important thing. And now we're moving into an area where we need application program support. We'll talk more about that soon. The hardware is still in its early development phase. The initial groundwork was done by the NVDIMM. And for those who are unfamiliar with what that is a standard memory stick, a DRAM module, but it's got flash backup on it, so it's got a little extra on there. And it was deeply investigated in an NVDIMM report that Objective Analysis, my company, put together. Anybody who downloads the slides can see something that tells a little bit about that report. But it did require significant amounts of changes. It needed to have BIOS changes so that the computer would know that it could do a reboot without having to reload everything from the SSD or the hard disk drive. And then a power fail signal had to be brought to the DIMM. And all of that had to be standardized. That is now part of the DDR bus spec. 3D crosspoint memory is also driving hardware changes, and that's for two reasons. One is that it writes more slowly than it reads, and the other is that it's not the same speed as DRAM, and so the bus needs to be able to handle that. But we have seen new technologies arrive to support that, and Cadence is an early supporter of an MRAM DDR4 specification. That's to support something that Everspin is producing, that is a DIMM that's got MRAM on it. It doesn't need refresh like DRAM DIMMs do, but it also needs a little bit of a different handshake, and that's something that Cadence is now supporting. So people who want to put together ASICs and FPGAs that support that DIMM can do it. So, you know, we've already seen some groundwork in there. Next slide. There's still ongoing requirements, though. I talked about the fact that Optane didn't write at the same speed as it's read, and so because of that, you've got different memory spaces, and that's what's called a non-uniform memory architecture. That requires the redesign of the memory management unit for that, so that the MMU actually understands where the Optane is, or where other persistent memory is. And that has been incorporated in Intel's Cascade Lake processors, which I never remember what the long name is for that. It's second generation something. But we also need, in order to use this effectively the way that storage has been used, we need faster context switches. For the meantime, because context switches are so slow, the industry is using polling, where the processor just sits in a loop and waits until the slower memory is done with whatever transaction it needs to do. And it's also handled by an updated DDR4 bus that is a transactional bus. It handles out-of-order processing, where you can actually give a write and then perform a couple of reads before you get an acknowledge for the write. And that supports non-deterministic access time. So all of that hardware support is going into play. Now, Tom's going to talk to you about the software side of things.
Indeed, I will, and I hope that the sound issues that people were talking about earlier are better now. I've tried to move our microphone. So let's talk about the software. First of all, having persistent memory like this as part of architectures is going to require significant changes in a lot of different software, for instance, in the operating system. And SNIA for several years now has had been working on a persistent memory programming model. You can see the URL to find out more information about this. And it gives various ways in which the application can work with persistent memory at the kernel level, at the file level, and also directly with direct mapping between the application and the persistent memory device, which is sort of the holy grail where many applications would like to work, where they can work on the block level and directly address the memory. So this progress is being made on various of these software technologies. And in particular, some progress in 2019 and plans for the persistent memory for 2020 and beyond are, first of all, the hackathons, which Marty mentioned, which are meant in order to give people direct experience working with these persistent memory technologies and finding out how to program them and integrate them with other hardware, and also various workshops that SNIA is doing. There also is work on a persistent memory developers kit, which using persistent memory software interface specifications that have been created. And then, of course, next week, there'll be a lot more discussion, demonstrations, exhibits, etc., on persistent memory at SNIA's Persistent Memory Summit. And they're also up on the SNIA website are various white papers on these emerging memories, on solid-state memory in general, and in particular on persistent memory. In the future, there's work going on developing a remote persistent memory programming model that is remote direct memory access technology, and then updates to the current persistent memory programming model in order to support new applications. So persistent memory, of course, is useless if its advantage is not used. And one of the big difficulties, of course, is that this idea of a memory being persistent is unknown in most software, operating systems and other software as well. So it'll take a while for software to get updated to take into account the characteristics of persistent memory, and these new standards have been created. Closed systems can use it now where all parts of the architecture are controlled, for instance, in hyperscale data centers or in SAN and other types of storage hardware. Open systems where this truly is available and programmable are being developed now. So with that, I'll go back to Jim. Go ahead.
Okay, thanks. So I'm going to talk about the Optane DIMMs that just came out in April. This is a slide that a lot of people, I'm sure, on this call have seen before because I present it just about every time I have an opportunity. But what it shows is the bandwidth on the vertical axis and the cost per gigabyte on the horizontal axis of the various layers of the memory storage hierarchy. And so up in the upper right-hand corner, you have your caches, and then you move down to DRAM toward the center of the chart. And then black is SSD, hard drive below that, and tape. Each stage in the memory storage hierarchy has to be faster than the next slower stage, but it can be slower than the next faster stage. It also has to be cheaper than the next more expensive stage, but can be more expensive than the next lower stage. And, you know, things have to fit into that in order to make sense in a system. Something that doesn't go on this line doesn't. And the Optane DIMM has been targeted to fit in there where the blue dot is that I put 3D Crosspoint in, that it needs to be cheaper, and it needs cheaper than DRAM, it needs to be faster than NAND flash. The fact that it's faster than NAND flash is assured, and the cheapness is what Intel is working on right now. So next slide. So this is a key selling point for the next generation server CPUs, the Cascade Lake ones, because by combining the Optane DIMM with CPUs, they're able to get significantly more improvement in processing performance than they've been able to get just by processor improvements themselves. And Optane SSDs are getting some acceptance, but they're not getting anywhere near the acceptance we're expecting to see from the Optane DIMM. NAND makers are also trying to keep the Optane SSD from becoming popular by coming out with NAND flash SSDs that are doing extremely well. We do have a report on 3D Crosspoint that was introduced about 4 months ago and there are details at the end of this slideshow for people who want to see what our projection is for where this market goes and really get a better understanding for why and how this is an important part of memories. I'm going to turn it back over to Tom to talk about MRAM.
Yeah, so Jim just told us about phase change memory, 3D crosspoint technology, but there's another memory that's starting to be used in many applications, both data center, but also, interestingly, for IoT and various embedded industrial and consumer applications, and that is magnetic random access memory. And there are basically three types of magnetic random access memory, though it does seem like every few weeks someone comes out with a new memory technology, often involving magnetics, that might potentially could displace them. But the Everspin actually has been making an awful lot of what's called toggle mode MRAM. You can see the basic structure on the left-hand side here. Basically, a magnetic field directly switches a layer, which causes a change in resistance. And that is the basic memory. It's reasonably fast. It's been very useful for a lot of applications. Everspin actually has shipped over 123 million little chips of various sorts, most of them is toggle MRAM, and some now with the spin tunnel torque that are used a lot of caching and buffering applications. Now, the spin transfer torque is a technology that's going to have, looks like it's going to have some legs for some time to come. It's a lot faster than toggle mode. It's a lot smaller, and it seems to show scaling possibilities that several of the other, first of all, the conventional volatile memories don't have. It can shrink to smaller sizes, and it's also pretty quick. This involves actually transferring the spin from one side of a insulating tunnel junction to another side, and causing a change in the state of the material by doing that, and therefore causing a change in resistance of these two layers. Everspin is now shipping up to 1 gigabit spin tunnel torque devices, and this is generally the technology that all of the foundries are looking at as an option for internal memory in embedded system chips. But there is another technology that's in the wings in the research labs right now. And the interesting thing about this is that spin tunnel torque allows you to get speeds that are close to those of DRAM or the slower SRAM. But the spin orbit torque actually reverses a lot faster than the spin tunnel torque, which requires a thermal process to get the spin started moving. This one is done directly by application of a current. So it's a 3-terminal device. It potentially can be as fast or faster as SRAM. Is the fastest SRAM, and so this is a technology, although there are don't know of any commercial products out there right now, could come out and be part of this bestiary of magnetic random access devices that could potentially replace SRAM and provide a volatile SRAM replacement. So MRAM cache, the status is that MRAM cache right now made by Everspin is used in certain IBM SSDs, also has been used in some RAID controllers and other caching and buffer applications. There's Spin Memory is another startup besides Everspin that has something they call processional spin current, and they also have a technology for improving the endurance, which is pretty good in general for these MRAM devices, which they call endurance engine technologies. In actuality, like many of these technologies, you can change the process and the structure in order to do trade-offs between, say, thermal resistance, endurance, retention, and capacity of these devices. Everspin is still the sole supplier of standalone MRAMs. As I said before, they've shipped over 123 million units. And there's another startup called Avalanche, which is also been sampling for some applications. A lot of the applications today are niche markets, as we said before, some solid-state drive, even hard disk drives and RAID controllers, but also space, high uptime systems, and in general in caches and buffers. So this embedded MRAM on SoC, system on chips, or these embedded devices, most of the major semiconductor foundries have offered embedded MRAM as an option. some of them also have offered embedded resistive RAM technologies. But the ones who have said they would make MRAM available include Samsung, Intel, TSMC, Global Foundries, which actually manufactures Everspin's 300 millimeter wafers they use for their standalone chips, but also is using their technology for their foundry products, and then UMC. As we get more people making MRAM, even in these embedded applications, we'll increase the volume of the equipment made. And generally, it should help to improve yields and lower costs, which is a very important element, as Jim will get in later on when he talks about the business aspects of introducing emerging memories. Bringing the cost down by increasing volume and familiarity with the technology, whether it's embedded or standalone, is a critical element in being successful. And also new tools are needed for MRAM, which have their own capital equipment spending components. So the more of those tools that are made, the more volume there is, generally the lower cost of manufacturing gets to be. And our report that we'll just mention at the end of the talk here, in addition to looking at projections for emerging memories, and in particular for MRAM and phase change memory, looks at the capital spending expectations for MRAM. And here we show a high, median, and low estimate. And our median estimate is by the end of this decade, we could see over $800 million annual spend on capital equipment in order to meet the MRAM production requirements that we project. And with this, I'll turn it back to Jim, who's going to talk to you more about some of the business aspects of persistent memories.
Thanks, Tom. So yeah, let's the business conditions I say are in flux, and you'll see why in a second. So first of all, I've got two slides here. This first one is, who wants persistent memory if it costs more than DRAM? And this speaks to the NVDIMM market, the one that I was talking about before, where DRAMs are backed up by NAND flash. And so necessarily, this has to cost more than just a simple DRAM DIMM. And the people who are buying this at the higher price are people who make high availability systems where it actually allows them a nice, inexpensive way to provide high performance without losing data. Mm-hmm. Financial databases are very important with that, so that you don't end up losing a transaction because of a power failure. And then there are certain hyperscale applications that promise to use an awful lot of them in the future. We're also seeing some interest in MRAM DIMMs, like I spoke about from Everspin. They're faster, but they're even more expensive than the DRAM and NAND flash ones. This forecast that you see here shows two different NVDIMM markets. That's the dash P, which is basically Optane, and this is a forecast that shows that coming in a little bit later. And then NVDIMM-N, and that's the kind that I spoke about before, that was the DRAM with an NAND flash backing store. Moving to the next slide. The thing that's really going to cause the new memories, though, to take off is if their prices drop faster than the price of established memory technologies. And this is a chart showing roughly what memory prices are going to do, price per gigabyte, for several different existing technologies through 2030 by our projection. And so we're expecting to see DRAM level off sometime, or at least start to slow down in its descent. SRAM and NOR flash and E2PROM all at the top of the chart, they've already done that. And NAND flash we expect to continue on its decline, because nobody seems to know how many layers you can actually put on a 3D NAND. What's important is that the new memory has already crossed over the price per gigabyte of E2PROM, SRAM, and now NOR flash. And so the new memories, they do stand a chance of increasing their volume simply by cannibalizing the markets for established memory technologies. Eventually, a new memory could get cheaper than DRAM, and that's what Intel's plan is for Optane to become cheaper to manufacture than DRAM, so that they can sell it without incurring losses at a lower price. We don't see the new memory actually threatening NAND flash anytime soon, but could happen sometime in the far future. Next slide. So back to the second of those two slides that I told you had. Who wants persistent memory if it costs less than DRAM? Well, that's 3D XPoint. And we expect it to be very widely accepted because of the fact that it will be a cheaper way to get a huge memory on a processor. It improves cost performance, and in the near term, we're not expecting persistence to be the major selling issue. We expect instead for the size of the memory to be what it will do. That will drive the success, but then as the application programs that Tom told you would come for persistent memory, then that will actually get in there. And what this chart on the right shows is the DRAM, I'm sorry.
The NAND price.
Yeah, DRAM to NAND price ratio. That's an example of how this dynamic has worked. NAND flash actually used to cost more than DRAM. And once its price crossed over in 2004, then that ratio kept expanding and it drove the success of SSDs. We're expecting to see a very similar kind of dynamic happen with Optane memory or with any other emerging memory technology that goes after the DRAM market and is capable of getting its costs down low enough that it will end up taking market away from DRAM. But, you know, something that factors into all of this is that DRAM prices are not stable. And we've had a pretty darn big price collapse over the past year where we've seen a 55% drop, you know, actually down to the bottoms of those little troughs at the right-hand side of the chart. We've seen a 59% price drop in, sometimes with DRAM. That means that if something is going to sell cheaper than DRAM, then it's got you know, a very difficult road ahead of it. And that has proven difficult with the emergence of Optane memory. So let's move to the next slide. And this shows why we have those price collapses. And this is something that a lot of people say, oh, we'll never have another collapse again. But, you know, the market always follows the same thing. When there's a shortage, DRAM prices stabilize. The manufacturers are profitable, and so they invest in extra capacity, and they invest too much. And so that causes an oversupply a couple of years later. Prices collapse, and so they shut off their investments, and that means that they're under-investing, and eventually demand catches back up to supply, which goes back into a shortage. So as long as we're using DRAM, we're going to have these cycles, and those cycles are going to influence the pricing of whatever it is that goes in between NAND flash and DRAM.
So it's sort of memory karma, huh?
Yeah, comeuppance. So persistent memory competes against established technologies. 3D XPoint has to be cheaper than DRAM in order to make sense of systems. MRAM has to take up less space on a die, the way that Tom was talking about in embedded applications, than SRAM. And those are the ways that they're going to get in, is that they've got to offer some price advantage to the end user. And whenever there's a DRAM collapse, it undermines the pricing of 3D XPoint, even though 3D XPoint is sole source, which kind of goes against the grain of the way that things go in the semiconductor market, because usually sole source products have very stable pricing, but not in this case. This is a chart of the profitability, the net profit of the companies that make DRAM and NAND flash. And the reason I'm showing this is that in 2017 and 2018, the NAND flash market did very well, the DRAM market did very well. 2018 was actually when NAND flash started to falter. But what's more important is what happened with DRAM, is that you had huge profits in DRAM, and Intel was selling Optane against this, and they should have been profiting from their NAND flash, which is sold out of the same division. So the blue bars are the Intel non-volatile solutions group profits, which compares very well against what the DRAM and NAND flash manufacturers or the other manufacturers on this. And you can see that while everybody was profiting in 2017, 2018, Intel was incurring losses, and there was only one quarter, the third quarter of 2018, when Intel was able to make a profit. That was when DRAM prices were extraordinarily high. This is because they're actually selling Optane memory at a loss. And until they get the volume up high enough, they're going to have to continue to sell it at a loss. And this is something that it pretty much only makes sense for Intel, because their sales of Optane, especially Optane DIMMs, are an enabler for processor sales. They can use profits from the processors to offset the losses from Optane. And so that's kind of a predicament for them, but it's not a long-term thing. It will eventually solve itself. So we're expecting to see shipment growth in new memories. This chart actually shows gigabyte shipment on a log scale of DRAM, NAND flash, 3D XPoint, and MRAM. And we're expecting, because of the fact that Intel is investing heavily and because there is great appeal with 3D XPoint DIMMs, we're expecting to see very solid growth with that. And with MRAM, we think that it's going to be a good technology that's going to fit into an awful lot of embedded applications, that it's going to replace a good bit of NOR flash and SRAM. And so it has also, a good chance of success. And the emerging memory market, for the forecast that we put in our report, should grow to over $37 billion by 2029. With that, I'm going to hand it back over to Tom.
And Tom is going to bring us in on the home stretch here. So more work is needed, of course, on this technology, particularly with persistent memory. You pointed out that application support and software in general for persistent memory, a lot of work is still to be done on that. Open source libraries to support persistent memory and a persistent memory development kit are needed. Hardware support for persistent memory outside of Intel, we need more of that. And as I mentioned before, and as Jim pointed out in his business model, the success of these emerging memories to take their place in this hierarchy of memory technologies requires that these technologies ramp up. Ramping up will reduce the total cost of manufacturing and the cost per part, which will make them less expensive and drive even more use. So there's a virtuous cycle in increasing manufacturing volume, finding new applications. For instance, we mentioned these embedded products, although maybe a lot of the SNIA members aren't involved. There's a lot of interest in doing AI inference engines at the edge and at endpoint devices using this technology because a lot of times these things may be running on battery or power constrained, and persistent memory like MRAM, you can turn them off and turn them back on, and it's on instantly. It preserves the state, and you can save power that way. Also, we need to standardize our remote persistent memory protocol. We talked about that earlier. And then, of course, if you're going to really be good at this stuff, you should know what you're talking about. Jim and I can help you to understand this industry and its market. So with that, we're open to taking questions now. We've got a few from the audience.
So we have two. We have two questions. We have two questions from the audience. So the first one is for you, Tom. Going back to your MRAM presentation, asking how MRAM tools are different from what's been found in fabs before.
Yes. Well, first of all, magnetic random access memory manufacturing involves different materials that are used in conventional CMOS processes. In particular, the magnetic materials are different. And so there's going to be differences in some of the deposition technologies in order to make these materials with the right steps. Magnetic fields may need to be applied during the processing. But what really is different is the patterning technology using ion beam etching, which is not conventional used. And right now, these MRAM devices are made in the back end of the line on the CMOS chips. And part of that is because of some of these unique processes like the ion beam etching that are used to make MRAM. As MRAM becomes more common, there are possibilities of making even more changes in the MRAM technology to bring it even closer into the CMOS processes themselves potentially.
Thanks, Tom. And Jim, there's a question for you as well. Do you expect NVDIMM-P to be priced more than DRAM? And if you do think so, why is that?
So there is NVDIMM-P and there's NVDIMM-P. And when that nomenclature was first devised by JEDEC, they were hoping that the Optane DIMM would fit into it. But Intel has kind of gone off in their own direction with that. And that particular device, the Optane DIMM, is going to be sold at a lower price than DRAM. The NVDIMM-Ps that should sell at a higher price than DRAM are more along the lines of Everspin's DDR4 MRAM DIMM. And I don't know what the exact price is for that, but if it's in line with any of the other pricing that Everspin does for their basic chips, it's considerably more than what a DRAM costs. And yet they've got customers, people are interested in that, and that's, you know, the case that I talked about where the customers who are buying those look at what the overall system cost is, and if they can make a savings by using that, then they will.
Oh, and I just remembered something on the MRAM equipment. So I talked about the process equipment, but also some of the test equipment is going to be different with MRAM. In particular, when depositing these magnetic films, the initial structure before the patterning, there's special process or test and measurement equipment that may be needed, at least to develop the process for making these parts. And then there's some differences in the final test as well, but it's a lot more on the test side, on the blanket deposition side. So we got some more questions here.
We do. Let's do this. Let's do the shorter one first, and this is for both of you, I think. So, what do you think about CXL and persistent memory? And if you would do a quick definition of CXL for our audience, that would be appreciated.
You bet. Okay, so CXL is it's a high-speed CPU interconnect. I think that's what they're talking about. That enables more efficient performance in the CPU and the platform enhancements and workload accelerators. It's also an open industry standard. So this is potentially replacing some of the proprietary interconnection schemes. And actually, I've seen some stuff where they talk about this in connection with heterogeneous integration of chips in various sorts of technologies. And some of this is related to bringing memory and computing closer together. I think that these various persistent memory technologies, call them generally that, these non-volatile emerging memories, will play an important role as part of, that CXL will be an interconnection technology that will be used with chips that contain these persistent memories, or in fact are a standalone persistent memory application in the case of some kind of heterogeneous structure where you're building multiple chips together into a device with close integration of all the different aspects. So hope that's
something. Yeah,
go ahead, Jim.
Something to keep in mind though is that these interfaces are just the same way that a DRAM can be offered in both DDR4 and in DDR5. A memory chip can be offered with different interfaces. And so if CXL takes off, then these technologies should be able to support it. And if for some reason CXL does not take off, then these technologies can go with whatever interface lends itself, whatever interface is accepted. So I don't think that there's anything about the emerging memory technologies that really determines the success or failure of CXL, and vice versa.
Well, I think though that if we're right that these emerging memories like Optane and 3D Crosspoint and MRAM become important elements in the whole hierarchy of memory technologies and allow the use of non-volatile versus volatile memories, that CXL, if that is true, then CXL will need to be able to work with those persistent memories. So that much I think probably would be true.
I just wanted to add, Tom and Jim, that in next week's Persistent Memory Summit on Thursday, January 23rd, there'll be a presentation on CXL and persistent memory from Stephen Bates from Idedicom. Many of you know Stephen, so he'll be covering that in a 30-minute session in the afternoon. And I know Tom and Jim will have some comments on Stephen's presentation because Tom and Jim are doing the recap, and the wrap-up at the end of the day at the PM Summit. So hopefully you'll be able to attend. If not, all the presentations and videos will be available live on the SNIA website. So let's move on to RRAM. There's a question that came in on RRAM, kind of similar to what you were talking about, Tom, on MRAM. Could you comment on the impact of RRAM in the PM space?
Sure. So RRAM is another. First of all, RRAM actually RRAM stands for resistive RAM, sometimes also RERAM as an abbreviation. It actually is a broad category that includes several different types of memories, but usually when people specify it as resistive RAM, there's either a filamentary type resistance change by forming and disassociating filaments that interact with each other to create more resistivity or less resistivity, or by a change in ionic content within a device. So those are what people usually talk about as these resistive memories, because in actuality, a lot of the memories, including phase change and MRAM, involve changes in resistance. So, but if we do talk about those type of MRAMs, the ionic and the filamentary type technologies, there are foundries that have made commitments to provide resistive memories as well as an option, besides what we talked about earlier as the MRAM technology. So I think it's going to have an impact. In a sense, we've sort of said that if resistive RAM takes off, it's probably going to need similar sorts of capital requirements, in a broad sense, although different technologies as MRAM. The second part of that question actually is about Everspin, the fact they don't have a huge market cap, how will they make the investments? Well, that's where the partnerships come in. Everspin in particular made a deal 2016, if I remember, with Global Foundries, which is one of the larger foundry companies, to actually manufacture 300 millimeter wafers, both for Everspin for their standalone products, which they make out of those wafers, as well as licensing to be able to provide that technology to Global Foundries customers for various applications.
Embedded
applications in particular, and they've been actually doing a lot of work on automotive embedded applications, which can help in driver assist technologies and other sensor fusion and other capabilities within automobiles, and to replace currently used memory technologies. So I think the answer is that they're not doing it alone, that these companies, and including other companies like Spin Memory, have partnerships with major companies that manufacture semiconductor devices, foundry companies, and therefore that the investment is not just on their part, but it's also on the part of their partners.
One thing that I'd like to say too is that when we were putting together the report, the emerging memory report, we could have forecast that all of those, 20 or so technologies that we were looking at, how big the market would be for each one of those things. But that's not really what's going to happen. What's likely to happen is that one technology is going to win out and get the economies of scale, and the other technologies are not going to be able to get it. We chose MRAM as the one that we were going to talk about, but that was just because we had to choose one. It's still a little bit early to tell which technology is going to be the real winner.
There's another question, whether this presentation is going to be available, and Marty, I think the answer is yes, isn't it?
It will be. I have a slide coming up that'll show you exactly where to get it, but we have a few more minutes, Tom and Jim, so hopefully we can answer some other questions. This goes back, the next question goes back to software, your software discussion about what kind of tools, language, and compiler support do you think is missing in order to fully exploit persistent memory? And should programmers play a role in exploiting persistent memory?
Oh, first of all, the answer to the second part is yes. Programmers should play a role because it's new programs that are going to be required that are persistent memory aware in order to implement these applications and drive use and therefore volume, and therefore reduce the price, creating more use. And programmers should know something other than DRAM exists, and that's part of why we're doing calls like this and why SNIA has this persistent memory activities going on as well. So go ahead.
Yeah, the takeaway, if I'm guessing that a programmer wrote this question.
Yes.
And the takeaway is if you as a programmer are going, not just, allowing virtual memory to manage the whole thing for you, but if you're instead actually saying in your application program that certain things need to be written to disk now because it's important, then that's the kind of a place in your program where you're going to say, I'd like it to be written to persistent memory now, because that kind of thing, which is used in transaction processing systems and other highly sensitive things, the programmers will push things into a persistent media, into an SSD or into a hard disk drive, in order to assure that if there's a power failure during the course of a transaction, that power failure doesn't cause the transaction to go weird. And so that kind of programming will be able to take advantage of it, application program, and it will be able to use these new SNIA calls to accomplish that. And those SNIA calls, they are just OS calls. I don't know if compilers or support is required for that, as far as I understand software, which isn't very deep. I think that those calls can actually be made by the programmer themselves. But however they're made, the application software is the thing that really needs to change.
So just to add to what Jim said, in addition to providing options, new ways of dealing with power outages, the use of these persistent memories to replace volatile memories also gives you the capability of lowering your power usage. And that may be important in some data center applications, but particularly as we move to some of these advanced networks, 5G and stuff, we build stuff out on the edge. Some of those edge applications, and even at the endpoint, even for enterprise or industrial as well as consumer applications, may be running on batteries or energy harvesting of some sort. Having the capability of turning things off when they're not in active use and being able to turn them on instantly without having to reload memory will be a great advantage for those products as well. So I think new options for the way you handle power failures is one important element that the programmer should be aware of and build their programs around. The other one is new ways in which to save power and have a greener data center, or be able to operate in places and in environments that you otherwise would not be able to by using these persistent memories.
Thanks, John and Jim. We have two more quick questions because we have about 10 minutes left. So the first one is about Micron, which you haven't really mentioned, their X100. How do you feel that's going to impact the 3D XPoint market?
Yeah, I just wrote a post on the X100 a couple of months ago, actually, on this was for the for the SSD Guy blog. And the X100 is, Micron brags that it's the highest performance SSD on the market, and that it's a few times faster than the Intel Optane DIMMs. And I'll take them at their word for it. What that means for users is that now there's an alternate source to Intel. And so there can be competitive pricing. On the other hand, since Intel is already selling at below DRAM prices at a loss, then I don't think Micron's going to need to compete that much on price. But they've got a very attractive product. I'm expecting for it to take market away from the Optane DIMM, from the Optane SSD, not the Optane DIMM.
Yeah.
But the Optane SSD, for reasons that are explained in another SSD Guy post, is not all that fast because the NVMe interface and the programming stack slow it down. And so this is a kind of a funny niche, and I'm not expecting for crosspoint SSD, the crosspoint SSD market to get very large. In my 3D crosspoint report, I actually basically ignore the market for crosspoint SSDs and focus on my forecast on the market for Optane DIMMs or for 3D crosspoint DIMMs, because that's the application that makes the most sense. So although this is a really good product, I'm not expecting it to play into a huge market, but I do think that it will give Intel's Optane SSDs a run for their money.
And it's second source, so give customers new choices.
Perfect. So the last question we have before we go to the closing slide is, where do you feel that RRAM and NRAM stand in the overall emerging memory space?
Well, the NRAM, I believe that's the carbon nanotube, and it's another type of resistive memory. I didn't talk about that before. As I said, resistive memory actually could be a very large class of things. There's technologies, particularly a company, Nantero, which has been developing this carbon nanotube as a resistive memory, and they're out there on the market and doing demonstrations.
Yeah, they're doing demonstrations. I don't think they've sampled.
I don't think there's any commercial samples, but if there are, Jim and I would certainly love to hear about it. But but in a sense, we've got sort of a golden age of memories right now, emerging memories, that we have a whole great variety of different approaches that people have been taking. And I think part of what it points out is the importance of memory, and storage too, for that matter, in computation. It's just it's a key enabler of modern computation, and these new memories will enable new ways in which we can process information in more places with varying latencies, and for more applications that can serve human beings and help to generate wealth. So
there's certain RRAMs though too that are available. Mitsubishi's got a microcontroller with an RRAM in it. Crossbar has been working with a couple of other companies for embedded RRAM.
For enterprise.
They've had some success. Yeah, but they like to show off a certain system that's based on their RRAM, which does image recognition.
There's a lot of neural networks. Actually, that's another thing we didn't include here is the computing applications of some of these emerging memories. Is that there's a bunch of neural network technologies that are built around resistive memories and phase change, and I think even one or two I've seen with magnetic random access or spin-based devices, for example.
Yeah, so they're there. It's
another webcast.
Well, I'm not so sure it would be a SNIA webcast. This neural net stuff is from SNIA's area of specialty. But the important thing is that what's shipping in the highest volume right now is MRAM, and surprisingly enough, ferroelectric memory, which we only just barely touched on.
Right.
And the RRAM is just beginning to emerge. We haven't seen enough NRAM that we can really tell very much about it.
Right. There's a lot of niche applications for many of these memories. It's kind of what Jim was pointing out. For instance, ferroelectric RAM is actually used in a number of like card applications,
RFID cards,
things like that. Or and you can make flexible ferroelectric memories. So some flexible electronics are using ferroelectric memories.
Yeah, you're talking about thin film.
Thin film memory. Yeah. And likewise, there's been various types of resistive RAM chips that have been out there for specialized applications for some time. There's a bunch of niche markets that many of these memories have been, providing some volume, not a huge amount of volume, but they serve important applications. And sometimes they're the best option for that application. For instance, something that's in a high radiation environment, like in outer space or a nuclear reactor or something.
Well, I think we'll stop here, Tom. We'll go ahead and stop here.
Okay.
Just wanted to let everybody thank you for watching our webcast. Please rate it. We'll have a blog with the Q&A up shortly, but check out these resource links. So we have Persistent Memory Summit videos and presentation slides, and that's where you can find the presentation if you click that link. We also have a complete educational library with 2,200 resources on persistent memory and many other topics, our blog, and then our persistent memory activities with the technical work group and our persistent memory and MVDIM special interest group, and then the programming tutorial and the hackathon program. So these are all click-through links, and we hope that you'll take advantage of them, and we hope to see you next week or online at our next webcast. Thanks again for attending, and we'll see you soon.
Thank you, Marty.
Thanks.
Thank you, Tom and Jim. Bye now.
And thanks, everybody, listening.